Welcome back. In our previous lecture, we delved into the history of classical mechanics and Newton's first law. Today, we'll build upon that foundation by exploring Newton's second and third laws of motion and the crucial concept of momentum. But first, it's important to understand a key principle. Internal forces within a system cannot cause the system as a whole to accelerate. Imagine you're inside a sealed box. Inside this box, there are two blocks connected by a compressed spring. If the spring is released, it pushes the internal blocks apart. Notice that while the blocks inside move, the box itself, representing our entire system, does not accelerate. Its center of mass remains in the same place. Internal forces act between objects within a system. They cause changes in the relative motion of parts within the system, but the net internal force on the system as a whole is always zero due to Newton's third law, which we'll cover shortly. Therefore, only external forces can accelerate the system's center of mass. With that clarified, let's dive into Newton's second law. Newton's second law of motion provides a quantitative description of how forces affect motion. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Mathematically, this is most famously expressed as F net equals ma, where F net is the net force, m is the mass, and a is the acceleration. Let's break this down. Imagine we have two blocks, one light, say 1 kilogram, and one heavy, say 5 kilograms. If we apply the same amount of force to both, the lighter block will experience a greater acceleration compared to the heavier block. It speeds up much faster. Now, consider the same block. If we apply a small force, it will accelerate. If we apply a larger force, it will experience a greater acceleration. The direction of acceleration is always in the direction of the net force. Newton's second law can also be expressed in terms of another very important concept called momentum. Momentum, often denoted by the letter P, is a measure of mass in motion. It's defined as the product of an object's mass and its velocity. So, P equals mv. Since velocity is a vector, momentum is also a vector pointing in the same direction as the velocity. A heavier object moving at a certain velocity has more momentum than a lighter object moving at the same velocity. Think of a bowling ball versus a tennis ball, both moving at the same speed. The bowling ball has much more momentum. Similarly, a fast-moving object has more momentum than a slow-moving object of the same mass. Now, how does this relate to Newton's second law? Newton originally formulated his second law by stating that the net force acting on an object is equal to the rate of change of its momentum. So, F net equals dp by dt, the derivative of momentum with respect to time. If the mass of the object is constant, we can see how this leads back to F equals ma. Since P equals mv, then dp by dt equals d by dt of mv. If m is constant, it comes out of the derivative, so we get m times dv by dt. And what is dv by dt? That's acceleration. So, F net equals ma. This momentum formulation is actually more general because it also applies to systems where mass changes like a rocket burning fuel. Finally, let's discuss Newton's third law of motion. Often summarized as for every action, there is an equal and opposite reaction. More precisely, it states that if object A exerts a force on object B, then object B simultaneously exerts a force on object that is equal in magnitude and opposite in direction. These forces always occur in pairs, and they act on different objects. Let's see some examples. If you push against a wall, the wall pushes back on you with an equal and opposite force. That's why you feel the pressure on your hand. Consider a rocket. The rocket expels hot gases downwards, action. In reaction, the gases push the rocket upwards, propelling it into space. When two billiard balls collide, ball A exerts a force on ball B. Simultaneously, ball B exerts an equal and opposite force on ball A. It's important to remember that these action and reaction forces act on different objects, so they don't cancel each other out for an individual object. So, to summarize Newton's second law, F equals ma, or F equals dp by dt, tells us how forces cause changes in motion and momentum. Newton's third law explains that forces always come in action-reaction pairs acting on different bodies. Understanding these laws is fundamental to analyzing almost any physical situation involving forces and motion. Thank you for watching.